In this video, we're going to talk about bonding and how atomic orbitals overlap to form bonds. So, for example, if we look at two hydrogen atoms, and we're going to take two hydrogen atoms because they only have one electron, so this gives us a case where we only have one electron to deal with, and we're going to figure out how the one electron from each hydrogen contributes to form a bond. So if we have our two hydrogen atoms, each of them have a 1s shell, and it only has one electron to start with, so it only needs a 1s shell. And our second hydrogen also has its 1s shell. So when these two overlap, these 1s shells have to overlap, and in between there we get a bond where the electrons are being shared. So this bond, where the electrons are being shared between two atoms, is called a sigma bond. It's a covalent bond where the highest electron density is between the two atoms, and we have a bond axis here where the highest electron density resides. That bond axis is between the two hydrogen atoms, or whatever element we have. Now, when we get to a case where we have atoms that have more than just a 1s shell, they have a 2s, 2p, and so forth, it doesn't really work to just overlap the atoms. And the reason for that is if you think about something like carbon, carbon has 6 electrons, which means it has an electron configuration of 1s2, 2s2, 2p2. And these 4 electrons in the 2s and 2p shells are valence electrons. So we have the 2 electrons in the 2s shell, and 2 in the 2p shell, and then an empty 2p orbital. Well, if we try to overlap orbitals this way, the 2s shell is already full. So we could really only form bonds with these p orbitals, which at most would only allow us to form 3 bonds. And we actually only have electrons in 2 of those orbitals, so we could really only share electrons from these 2 orbitals. That would limit carbon to forming 2 bonds, which doesn't really work. It doesn't really make sense when you think about compounds like CH4. So what we do to allow carbon to form 4 bonds is we undergo something called hybridization. Hybridization is a mixing of atomic orbitals that generates a new set of orbitals that are able to form covalent bonds. So we start with a 2s and 3 2p orbitals. These hybridize to form sp3 orbitals. And these sp3 orbitals have both s and p character. So we get 4 sp3 orbitals where we put 1 electron from each of the 2s and the 2p orbitals. So we split these up, 1 electron in each orbital. Now carbon has 4 sp3 orbitals. If we take our hydrogens, which have 1s orbitals, those hydrogen 1s orbitals can overlap with the 2p orbital, with the sp3 orbitals of carbon and form bonds. And we get a sigma bond where one of the electrons from carbon's sp3 orbital overlaps with one of the electrons from hydrogen's 1s orbital. So sp3 orbitals are formed by mixing 1s and 3p. So this allows us to form a tetrahedral geometry with 4 things bonded to each of the sp3, 1 thing bonded to each of the 4 sp3 orbitals. So we mentioned the sigma bond already. So in a sigma bond, the electron pair is shared in an area that's centered on the line that runs between the two atoms, the way that we showed on our first slide here. But what about a situation where you have a double bond or triple bond? When a double bond or triple bond, you also have a pi bond. A pi bond occurs when you have parallel p orbitals that share an electron pair, and that goes either above or below the sigma bond that joins the atoms. So a double bond always has one sigma bond and one pi bond. A triple bond would have one sigma bond and two pi bonds. So if we look at something like, we don't have it drawn here, but something like H2CO. So we have a double bond between the carbon and the oxygen. So if we mixed and formed sp3 orbitals, we'd have room for 4 things to bond, but we wouldn't really have a way to form the pi bond. So what we do instead is we take the 1, 2s and 2 of the 2 p's, and we form 3 sp2 hybrid orbitals, and then we have 1 p orbital that stays unhybridized. For our oxygen, we again mix the 1, 2s with 2 of the 2 p's, and we form 3 sp2 hybrid orbitals, and then we have 1 p orbital that's unhybridized. So these two orbitals will form the sigma bond between carbon and oxygen, and these two orbitals will form the sigma bonds between carbon and hydrogen. Oops. There we go. So these two hybrid orbitals will form a sigma bond between the carbon and the oxygen, and these two sp2 orbitals from carbon will form a sigma bond between the carbon and the hydrogen. These two p orbitals that are left will form the pi bond between the carbon and the oxygen. So we get one sigma bond and one pi bond. So a pi bond is a covalent bond where the electron density goes around instead of along the bonding axis. So we get this pi bond here between the carbon and the oxygen. So what if we then have something like CH2 where we've got a triple bond between the two carbons? Well, now we need 2 unhybridized p orbitals to form those pi bonds. So we only hybridize one of the 2s and one of the 2p. So we form 2 sp hybridized orbitals. And then we have 2 unhybridized p orbitals that are going to form the 2 pi bonds. So now we have a hydrogen that forms a sigma bond between each of the carbons. And then we have a sigma bond between the 2 carbons themselves, along with 2 pi bonds to form the remaining bonds for the triple bond. So a triple bond has 1 sigma bond and 2 pi bonds. Okay, so this is a table that shows you the hybridization based on the steric number. And I will give you a table in class that also has this information on it. So let's take a look at a couple of examples here. So if we have SF4, so sulfur has 6 valence electrons, fluorine has 7, times 4. 7 times 4 is 28. Plus 6 is 34. So if we draw sulfur with the fluorines around it, and we give everybody their lone pairs, we go through and count up, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, and we were supposed to have 34. So that means we likely have an expanded octet of sulfur. Now if we double check whether we've met our criteria to have an expanded octet, sulfur has an atomic number of 16, which is an atomic number greater than 12, and it's bonded to fluorine, which is highly electronegative, so we can have an expanded octet on sulfur. So if we put our 2 electrons on sulfur, that gives us a total of 34. So now we have 4 things bonded to sulfur, plus 1 lone pair on sulfur, which is a steric number of 5. So if we go back to our table, a steric number of 5 gives us a hybridization of sp3d, which means that we also mix a d orbital into this hybridization. So we have one s, an s orbital, 3 p orbitals, and a d orbital that are mixed into this hybridization. So let's try CO2. So CO2 we've drawn a few times at this point. So carbon has 4 valence electrons, oxygen has 6, and there are 2 oxygens, which is a total of 12 electrons from the oxygen, 4 valence electrons from carbon, which gives us a total of 16. So I'm going to go ahead and draw carbon dioxide with the double bonds, since we've seen it enough times to be familiar with that. So we've got 2 things bonded to the central atom. So if we go back to our table, that gives us a hybridization of sp. And the other way we can know it's sp is we've got 2 sigma bonds, but we've got 2 pi bonds, one between each of the carbon and oxygen. So we're going to need 2 unhybrid sp orbitals to form those pi bonds. So we end up with sp hybridization for carbon dioxide and sp3d for SF4. So we're going to stop here, and we will get some more practice with this in class. So I will see you in class.